Okay, so before we find the domain of a rational function, we have to review, we're going to review a couple of terms, one of them being a polynomial. And polynomials are functions, so we can call them polynomials or polynomial functions. And a polynomial function has the form a coefficient, so an is a coefficient, like a number, 3, 5, it could be a fraction or a negative number. N is a positive integer. And then, so it starts with a power on x. It's a positive integer, and it steps down by 1 until we get to here. So this is x to the 1, and here this is times 1. And remember that x to the 0, or any non-zero number to the 0 is 1. So we write that as 1, but it starts with a positive integer, or at least non-negative, and steps down to a 0 exponent on x. And then each coefficient has, or each x term has a coefficient. This an is called the leading coefficient. And the leading coefficient cannot be 0. The degree that's associated, the largest exponent is called the degree. So this is a polynomial of degree n, because n is the largest exponent there. And then the domain of a polynomial is all real numbers. Okay, now we're going to talk about a rational function. And a rational function is a polynomial divided by a polynomial. So P and Q are polynomials. We don't really talk about degree of the whole function. The top polynomial has a degree and the denominator polynomial has a degree, but overall we don't really talk about a rational function having a degree. We will compare the degrees of the numerator and denominator polynomials. The domain of a rational function is all real numbers except where the denominator is equal to 0. So we exclude those numbers where the denominator equals 0. Okay, so let's look at an example, and we want to find the domains of the following rational functions. So here we have our denominator, and it is equal to 0, so we take the denominator, set it equal to 0, and solve for x. So here we get x equals 4. So when x equals 4, we have 0 in the denominator, which is bad. So our domain is everything but 4. So when we write that in interval notation, we write it like this. So this is every real number except 4. Okay, now we're going to look at for the domain of this rational function. So again, we look at the denominator and we find out, our question is, when is this denominator equal to 0? So take the denominator and set it equal to 0, solve for x. And the answer to the question is, the denominator is equal to 0 when x equals 8. So don't let x equal 8. Our domain is from -infinity up to 8, and 8 to positive infinity. So there's the domain there. Okay, so here my denominator is a polynomial, but it's already factored. So when is this polynomial that's factored equal to 0? So we take each factor and set it equal to 0. So the denominator will be equal to 0 and x equals 5. And the denominator will also be 0 when x equals minus 4. So we don't want either one of these cases to happen. So x cannot be negative 4 and x cannot be 5. So what I'm going to do here is I'm going to go from minus infinity up to minus 4, skip over minus 4, go from minus 4 to 5, skip over 5, and go from 5 to infinity. So that would be my domain. Okay, here I take the denominator, so I'm looking for the domain, take the denominator and set it equal to 0. Now I have two choices. I can use the square root method. Take the square root of both sides. And don't forget that when you take the square root of both sides, you get plus or minus. So this is plus or minus the square root of 49, which is plus or minus 7. Another way to do it is to realize that x squared minus 49 factors into x minus 7 and x plus 7. Then I take each factor equal to 0 and solve. Either way, it doesn't matter. So x cannot be, so when x is 7, the denominator is 0. When x is minus 7, the denominator is 0. So my domain is everything but 7 and minus 7. So I go from minus infinity up to minus 7, minus 7 to positive 7, and then positive 7 to infinity. Okay, here, again, I want to find when the denominator is 0. Now this factors. If I don't realize that it factors, I can use the quadratic formula, but this is going to factor into x plus 7 and x minus 3. So I get x plus 7 equals 0, meaning that x equals minus 7. And then I get x minus 3 equals 0. And so when x is minus 7, I'll have 0 in the denominator, and when x is 3, I'll have 0 in the denominator, so don't pick those two numbers. We go from minus infinity up to minus 7, minus 7 to 3, and 3 to infinity. Okay, so I take this denominator and I set it equal to 0. And now we saw x squared minus 49 and a squared minus b squared factors. Oh, excuse me. So a squared minus b squared factors. A squared plus b squared does not factor. So if I try to do this using the square root method, what I see is that I'm going to take the square root of a negative number, which if I am looking for the roots of the complex roots of polynomials, that would be fine. But I'm looking for values to exclude from the domain. So our domain starts off with all real numbers. So this does not yield any real numbers that I need to avoid. So we're not interested in that. So we say no real solutions. And so our domain, since we don't have to exclude any values, remains minus infinity to infinity. And so another way to think about this is x squared is greater than or equal to 0. But when I take x squared and add a positive number to it, that's always going to be positive, okay? So I'm never, if I'm always positive, I'm never going to be 0. And so I can also think about the domain as it's all positive numbers. It's all numbers bigger than 49, bigger than or equal to 49. So I don't ever worry about crossing the x-axis and dividing by 0. So the domain is all real numbers. So that's another way to think about how to find the domain when we have all real numbers. Okay, so that was quite a few examples for finding the domain of a rational function.